Now let's talk about the effect of temperature on atomic spectroscopy. Is it important to control the temperature of the atomic spectroscopy, or it doesn't matter if there is a change in temperature? Um, First of all, let's talk about what is the role of the temperature in atomic spectroscopy. The temperature will determine the degree to which sample will break down into atoms, and it also determines the extent to which an atom is found in its ground state, excited state, or in ionized state. We only need atoms that are we only need first the element in its atomic form or as atoms. This is the first thing. And we also needed only the ones in the excited state. For atomic absorption spectroscopy, it's this the amount of light that will be absorbed is the one that will be used to excite the atoms and will be absorbed. So the more the amount of atoms that will be excited, the more the atoms, the more the intensity of light that will be absorbed. And for in the atomic emission spectroscopy, the more the excited the atom, the more the intensity of the light that will come, that will be emitted or will be measured. So the temperature must affect if it affects the fraction or if it determines the extent to which the atoms will be found in its excited state and its ground state, it must affect the intensity of the light that will be measured by the detector. So first of all, we have our electrons in their ground state, and as they absorb the energy, they will be excited into the excited state. So the difference in the energy here is the difference in the energy between the ground state and the excited state. And we have something called degeneracy, and this is specific for each state. So we have a degeneracy for the ground state and a degeneracy for the excited state. The degeneracy will differ depending on which ground and which excited state we are talking about. So there's something called Boltzmann distribution, and Boltzmann distribution describes the relative population of the different states at thermal equilibrium. So if there is an equilibrium, the ratio between the atoms in the excited state and the ones in the ground state, so these are like the number of atoms in excited state, and the n naught is the number of atoms in ground state. So we don't need to measure actually or calculate the number of atoms, but we need to calculate the ratio between the atoms in the ground, the excited state, and the atoms in the ground state. This ratio equals the degeneracy of the excited state over the degeneracy of the ground state times the exponential of delta E, which is the difference of the energy between the ground and the excited state. K, which is the temperature in Kelvin, and the K, which is the Boltzmann constant. This is the Boltzmann constant, and T is the temperature in Kelvin. That means that this ratio will change pending the temperature. So as we increase the temperature, this ratio will increase. So let's look at an example. So if we are talking about sodium atoms, in the excited state, the difference in the energy between the excited state and the ground state is 3.371 times 10 to the power minus 19 joule per atom. So this is the delta E between the ground state and the first excited state. The degeneracy of the excited state is 2, so G star is 2, and the degeneracy of the ground state is 1, so the G naught equals 1. Now, if we use the Boltzmann distribution, we will find that the ratio between the amount of atoms in the excited state over the ground state will equals 2 over 1, which is the G star over G naught, times the exponential of the difference in the energy, delta E, and then the Boltzmann constant times the temperature, which is 2600 calories. So at 2600 Kelvin, you will find that this fraction is 1.67 times 10 to the power minus 4, which means it's less than 0.02%. So less than the 0.02% will be in the excited state. If we increase the temperature by 10 degrees, so the temperature now is 2610 Kelvin, and then we then calculate this ratio, you will find it's 1.74 times 10 to the power minus 4. That means that by increasing the temperature by 10 Kelvin, the excited state population increased by 4%. However, if you look at the ground state population itself, it will be only reduced by a very tiny amount, because at 2600 the ground state population is 99.98%, so it's the vast majority of it is in the ground state. The change in the ground state will be very minimal. So, but for the excited state, it's increased by 4%. This tiny increase will not affect the atomic absorption spectroscopy, but will have a great impact on the atomic emission spectroscopy. Let's imagine that you are in a big stadium, and the big stadium you have like 50,000 spectators. And if all the spectators turn their mobile torch on, and then only 10 of them turned it off, okay, so you wouldn't actually notice these 10, but if we increase that and 12 of the people turned their torch off, you wouldn't notice the change. On the other hand, if all the 50,000 are turning their torch off and then just 10 of them turned it on, you will simply notice it. It will be very noticeable. This is more like the excited um, state, or more like the emission, where we have a dark background and you can see the light. So if we increase this number by from 10 to 12, it will be noticeable. So any slight increase in the population of the excited state will affect the excitation, or will affect the atomic emission spectroscopy, but will not affect the atomic absorption spectroscopy in the same way. This is why the controlling the temperature is very important for the atomic emission, and more important than controlling the temperature for atomic absorption spectroscopy.